Hello again, welcome to another video. This video is all about deriving the distance formula from the Pythagorean theorem. So let's go and see. We're going to discuss both the cases in 2 and 3-dimensional spaces. We're going to start with the easiest case, which is R2 or 2D. In R2, the distance between 2 points P1 and P2 is given by the following formula. We show it as D, which is distance, is equal to the absolute value of the distance between P1 to P2. The reason is we are putting it in an absolute value is because distance can never be negative. It can be 0, it can be positive, but it can never be negative. We can't really say like this pen is negative 10 centimeter. So this is the reason we're just using the absolute values. But our main goal is to show how we got this long way square root. Let's see. If I have the point P1 right here with the coordinates x1 and y1, and I have another point right there, which is P2 with the coordinate system, with the coordinates x2 and y2, then we are really interested in the distance between them. We can show this distance as d, or the absolute value of P1 to P2. We are actually looking for this length. The way that we're going to work out this problem is that we are assuming this d is the hypotenuse of a right triangle. So I'm going to make a right triangle where d is its hypotenuse. So I formed the right triangle, and those are the sides of that. So let's say this is the first side and this is the second side of that. Let's say this corner right here is the point A, and A has the coordinates x1, the coordinates x2 and y1. The reason I say x2 and y2 is because from the point P2, we are actually fixing the x value. So if you assume this is the x-axis, we are fixing the x value on the x-axis, and we are just lowering the point P2 down there to be leveled out as the point P1. So it's going to have the x component of the point P2, and it's going to have the y component of the point P1. That's why we showed the point A to be x2 and y1. That's why I'm going to say the first side, or this one right here, has a length of y2 minus y1, because the x component is fixed. The only change is in the y component. So yeah, that's why we just say it's y2 minus y1. And the second side is its y value is fixed. We are just changing the x value. So there's a change in the x component. So we're gonna say that the second side has a length of x2 minus x1. Then according to the Pythagorean theorem, if I have a right triangle, this is not really a right triangle, but I'm trying my best to form one such this, and this is C and this is A and B, then the Pythagorean theorem just states that C squared, which is the hypotenuse, squared is equal to the sum of the squares of the other side. So it's going to be a squared plus b squared right here. Now, my hypotenuse, or c, is the distance, or d. So d squared is equal to, so this is going to be my a. I'm going to use this guy as my a. Then it's going to be x2 minus x1 all squared, plus this is my b. So the first side is b. It's going to be y squared, y sub 2 minus y sub 1 all squared, is equal to d squared. Then the only thing that we can do is just square root both sides. We're going to get d, or basically the square root of d to the 2 is equal to the square root of x2 minus x1 all squared plus y2 minus y1 all squared. And this side is going to be just d, or basically positive and negative d. But since distance can never be negative, we are only interested in the positive sign of the distance. And that's all about 2D. This is pretty much the same idea as 3D or 3-dimensional space, but let's just see how things are going to change. Well, things are going to get a little bit perspective because we are changing the perspective a little bit. So rather than seeing things as a flat surface, so instead of seeing everything on this board, we are seeing everything in a room. So we are assuming that the points, in addition to the x and y values, they also have the z value. So yeah, this is pretty much the difference. But let's see how we can prove things out. So let's assume that I have a rectangular cube, or rectangular box like this guy right here. Not a nice drawing, but I tried my best. So let's say this is a point P2 with the components x2, y2, and z2, and this is the first point P1 with the components x1, y1, and z1. Then the distance between those 2 points is the length d, which connects the points P1 to P2. So the thing that we're gonna do is that we are just lowering the point P2 over here then this point going to be the point P3, and P3, since it's going to have the same x and y components as the point P2, then it's going to be x2 and y2, but it's going to get P1's z component because it's going to be the same level with the same depth. That's why it's going to get its z value. Then let's say this was side 1 from the previous R2 or 2D example, and this is side 2, and this is side 3 over here. The side 3 is just z2 minus z1. Side 1 is, from the previous example, is y2 minus y1. Side 2 was x2 minus x1. Then p2 to p1, if I show it as d prime, then d prime is exactly going to be what? Going to be this guy right here in R2, right? So d prime was what? Was the square root of x2 minus x1 all squared plus y2 minus y1 all squared. Then this guy right here is actually a right triangle, right? So let's say d prime and the side 3, they form a right triangle. Then we can actually state the Pythagorean theorem for this triangle. Then d going to be what? Going to be the hypotenuse. So d squared going to be equal to d prime squared plus the side 3 all squared. So d squared going to be what? This guy all squared, which is going to give me the same as this guy right here. So to make my life easier, I would just copy and paste this one. Here you go. This is for d prime squared. And for the side 3, I would just add what? I would just add z2 minus z1 all squared. But now, this is in terms of d squared. Now I'm just interested in the distance d. Then I would just square root both sides, and I'm going to end up with x2 minus x1 all squared plus y2 minus y1 all squared plus z2 minus z1 all squared. Here you go. We just proved that. Let's just see a practical example and try to solve it. This is really easy to do. So by just recalling the formula, we can just solve this one. So we have the point P1, 1, 2, 3, and the point P2, 4, 5, 6. So the distance between those 2 points going to be the square root, or let me just draw it in a better way. Yes, much better. So let's just identify. So I have the point P1, which is 1, 2, 3, and the point P2, which is 4, 5, 6. So this is my x1, y1, z1, x2, y2, z2. Then according to the formula, it says x2 minus x1, so x2 is 4 minus 1, so 4 minus 1 all squared plus y2, which is 5 minus 2, all squared plus z2, which is 6 minus z1, which is 3, going to be 6 minus 3 all squared. This is going to give me the square root of 4 minus 1, which is 3 squared, going to give me 9, plus 5 minus 2, going to give me 3 squared, which is 9, 6 minus 3, going to give me 3 squared, which is 9, then this is going to give me the square root of 27. That's all. This is the distance, or this is the absolute value of the distance P1 to P2. In the next video, we will use this idea and try to extend it a little bit more to derive the equations of spheres and circles. See you next video.